Welcome to the next part of section 2.2. Here we are going to be discussing how we compute volumes of shapes that aren't necessarily cylinders. So last time we talked about how to compute the volumes of shapes that are cylinders, and we said the basic premise is that if you know the area of the base of the cylinder, maybe that's A, and you know how tall your cylinder is, maybe that's H, then the volume of the cylinder would be A times H. And so what we want to do now is we want to think about, well, how do I talk about shapes that aren't cylinders? So we'll start with thinking about the volume of a square pyramid. Remember that a square pyramid is a solid which has a square base, and each of those vertices of the base is connected to a single vertex at the top, forming a shape that looks something like this. Okay, so maybe we want to also give our square pyramid some dimensions, because certainly the dimensions of the square pyramid affect its volume. So let's call its side length of its base A, and let's call its height, in tradition with heights, H. So we have some square pyramid here. It has some base A and some height H. And in order to compute its volume, we're going to place it a little bit more precisely in three-dimensional space so that we can have access to coordinates, and we can think about coordinates of certain points and how we can compute volumes using the fact that we can assign numbers to points in space. So it shouldn't be clear how exactly we want to arrange this in three-dimensional space, but I'll go ahead and just start by saying how we're going to do it. So pardon my lack of drawing skills here. I'm going to be trying to draw some things in 3 dimensions, and not everything is going to work out exactly as I intend. So let's see. We're going to start by drawing our usual x and y axes here. And we kind of want to think about the... Oh, that's not great. We got to start over. Let's see. We want to think about the... There we go, that's better. All right, so we want to think about this as the x-axis and this is the y-axis. And there is kind of a third axis here you can think of that's perpendicular to both of them. This is traditionally called the z-axis. We're not going to be worrying so much about the z-axis here. We just want to think about x and y-axes, and we want to think about this as living in three-dimensional space. Now, the way that we want to place the square pyramid here is in a way that plays nicely with the coordinates. The nicest coordinate, of course, is the origin, the point 0, 0, and we are going to place the main vertex, the kind of point of the pyramid, at that origin there. So let's see. So that means that the square base is going to not be at the origin, and the way we want to place the square base is along the x-axis, so that the x-axis pierces the center of that square base. And I'm going to draw the square base first. So let's start here. Maybe it doesn't look so square, but in fact, it's intended to be square, and that won't be the worst mistake that I make. Great, so in order to draw the rest of this thing, we need to have the other edges. Cool. All right, so we have drawn a square pyramid. And maybe what we want to do in order to compute the volume is, rather than computing the volume, because we're not really sure how to do that, we want to approximate the volume using shapes that we know how to compute the volume of. Those shapes are all going to be cylinders. And the way that we're going to create some cylinders here is we want to think about these cylinders as essentially being cross-sections which are perpendicular to the x-axis. So here, maybe actually let's call this third axis z for the moment. So here what you want to be thinking about is that the cross sections of this square pyramid here, the blue pyramid that we've put in three-dimensional space, the cross sections of that thing should be parallel to the YZ plane. So trying to draw something like that, we would have maybe a cross section that looks something like this. Great. And we're going to use this cross-section here as the base of some cylinder. And we want to make that cylinder have small height in order to effectively kind of compute the volume. or in order to provide a good approximation to the local area there. So if we think about what this picture looks like in the XY plane, so right now I just want to kind of flatten this picture and look at it from the perspective of the z-axis. So I'm going to just draw out the XY plane here. Let's see, so my square pyramid, when I intersect it with the XY plane, is going to form a nice isosceles triangle here. If we wanted to talk about the dimensions of the isosceles triangle that we have, we know that the kind of right-hand side of the isosceles triangle here, that's part of the square base of the square pyramid. And so since the square base has side length A, we know that this height here in total is going to be A. Likewise, the horizontal dimension of this triangle is going to be the height of the square pyramid, and we know that height to be h. This green cylinder that I drew inside the square pyramid is going to correspond to a rectangle in the xy plane here. It's a little rectangle that looks like this. Perhaps it's not obvious from the drawing, but since I intended to use the left endpoint of this cross section here as the thing that determines the thing that determines the cylinder, I've used the left endpoint here as the thing that determines kind of the height of this rectangle here. All right, cool. So if we want to think about what's going on right now, what we want to do is we want to approximate the volume of this square pyramid by adding up the volumes of a bunch of these green rectangles, or a bunch of these green cylinders. I want to draw a cylinder here, I want to draw a cylinder a little bit to the right of it, and probably with a little bit larger square base. I want to draw a cylinder to the right of that and to the right of that, and I also want to draw a bunch of cylinders closer and closer and closer to the origin. So what's the process by which I'm doing this? Well, what I'm really doing here is I'm partitioning this interval from 0 all the way out to h. I'm breaking it up into a bunch of pieces, and then at each piece I'm placing one of these cylinders. So this should sound familiar in the sense that we are moving towards something that looks like an integral, and in fact we are. So if we are maybe thinking about partitioning the interval from 0 to h, then maybe what I want to do here is I want to find some formula that describes the volume of the kind of ith cylinder here. So we've partitioned the axis. The second thing that we did was we created some cylinders to approximate the volume. The third thing that we want to do is actually compute the volume of those cylinders. Well, we have an assumption about the volume of the cylinders. We know that they're going to be the area of the base times the height. Well, the height of the cylinder is exactly the length of this dimension here, which since we're partitioning this interval from 0 to h into a bunch of small pieces, we typically call that length delta x. So let's see, so the height itself is just going to be delta x. We also need to compute the area of the base. And in order to compute the area of the base, we have to think about, first off, what shape is the base? In this case, I know the base is going to be a square. The base being the part that I've outlined here on the square pyramid picture. Since that base is a square, I know that its area is the square of its side length. So I need to find out, well, what exactly is the side length that I'm looking for here? And in order to do that, I can go to my 2D picture, and I can recognize that the side length that I'm looking for is exactly this thing here. So I want to find how long is that side. The important thing is that it depends on the value of x. So maybe I want to say I'm looking at the volume of the ith rectangle here. So the left endpoint is going to be a point that I can call xi. So the last observation that I want to make here is, in order to compute the side length of this rectangle at xi, I have a couple of similar triangles here. One of those triangles is going to be formed by looking at this guy here, where I'm going from the origin up out to the two vertices on the blue triangle that correspond to xi. And the other triangle that I'm going to be looking at is just the blue triangle that I started with here. These triangles are similar triangles because all three of their angles are the same. They're both isosceles with the same interior, with the same angle here at the origin. And so what we can do is we can say that the ratios of their sides are the same. So maybe I actually want to think about the outer triangle as just the blue triangle. Great. So I've got the blue triangle and the red triangle here are similar. And what I can do then is I can say that the ratio of A to H here, being the ratio of this side to this side, has to be the same as the ratio of x, or xi here, to the height of this rectangle. And so maybe I want to actually give that height a name. Let's call it SI, being the side length of kind of that square that's sitting there. So SI goes from the bottom to the top of that blue triangle. All right, so let's see. So we have a ratio that we said we have here. Namely, we know that the ratio of A over H is going to be equal to the ratio of, what's the corresponding side to A here? The corresponding side to A is the side SI, and the side corresponding, or the length corresponding to H, is XI. And my goal was to have an idea of what the side length is. Well, I have a formula here. The side length of this green square is SI. So I can get a nice formula by multiplying both sides by xi, and I have AXI over H equals SI. So moving down, I can say that the area of the base, well, wait a second, the area of the base is the side length squared. But I have the side length here in terms of A, X, and H. And so I know that the area of the base is AXI out of H squared. All right, we're getting close. We have this nice formula here, area of the base times height. And what we want to do is we want to add up the volumes of all of these cylinders. All right, great. So let's use our sigma notation. We are summing over the number of cylinders that we have. We can suppose that number is n. We are adding up the volume of each cylinder, which we've said to be AXI over H squared delta X. And of course, you notice that this looks a lot like a Riemann sum. We're adding up some function of x. We are multiplying by delta x, and that's exactly what it means to be a Riemann sum. So the next step that we want to do is to take the limit as n goes to infinity. Look at what happens as these cylinders get thinner and thinner and thinner, and do a better and better job of approximating the volume of this square pyramid. So let's see. So what's happening here? Step 5. Take the limit as n goes to infinity. All right, so let's see. So limit as n goes to infinity of the sum from I equals 1 to n of AXI over H squared times delta x. Well, we know this is going to be an integral. We maybe don't know what the bounds of integration are yet, but we know we're going to be integrating with respect to x here. We know that the bounds on my x values are going to be since we're partitioning this interval 0 to h, we know that the integral is going to range from the x values of 0 all the way up to the x value of h. So I'm integrating from 0 to h here. And what's the function that I'm integrating? Well, it's ax over h squared. Notice here that this integral is okay because a and h are constants. They don't depend on x. If I had put any other quantities that did depend on x here, like let's say I put s being the side length, since s depends on x, this wouldn't be an integral that makes sense. But as soon as I only have my only variable here is x, this is an integral that makes sense to do. And now, great, we can actually compute this integral. So let's do that. We have integral from 0 to h of a squared x squared over h squared dx. I can integrate this. A squared and h squared are constants. The antiderivative of x squared is x cubed over 3. I want to evaluate from 0 to h. All right, so if I evaluate at h, so first that means replace all of my x's by h's. I only have the one x there, so this is a squared h cubed over 3h squared. I also want to evaluate at 0, so that's a squared times 0 cubed over 3h squared. The second term is going to be 0, and the first term simplifies. I can cancel out 2 of the h's in the numerator with both h's in the denominator to get a squared h over 3. Whew, all right, that was a lot of work, but in the end we have this nice formula which describes the volume of a square pyramid, just as long as we know the side length of the base, and we know the height of the thing. All right, so this is really nice. We've used calculus to figure out exactly how to compute the volume of some shape that wasn't a thing that we assumed. So that's really nice, but we would also really like to be able to do these problems without passing through Riemann sums. It would be nice if we could just go straight to the integral step and not have to worry about all of the setup work that we did to get there. So we're going to have a couple of steps for that. The first thing that we want to think about, this is a process that's known as slicing. And the reason that it's known as slicing is that we sliced up our square pyramid into a bunch of slices and added up the volumes of each of those slices. So the first thing whenever we want to compute volumes this way, the first thing that we want to do is going to be to place the solid on an axis. That was the very first step that we did previously as well. The second thing that we want to do, maybe let's take a look at the actual integrand here. This integrand, this ax over h squared, that was the area, the regular old two-dimensional area of one of the cross sections of this of our square pyramid here. If we took the YZ plane and we kind of slid it over to the right a little bit and intersected it with the pyramid here, we would have gotten some cross section that's perpendicular to the x-axis. So I'm even going to write not just on an axis here, let's put it on the x-axis. Part B then is going to be to find a formula for the area of a cross section formed by intersecting the solid with a plane perpendicular to the x-axis. It's okay, and in fact, it's hopefully true that the area here depends on the x value that you're at. The last step, C, is going to be integrate the formula, integrate the cross-section area formula using appropriate bounds on the integral. The reason that this process worked is the same reason that it worked for the square pyramid. You're going to be looking at these different slices, you're going to be taking the limit as their width, or as the height of each of those slices goes to 0, and that's going to give you a Riemann sum, and it's going to mean that you're integrating this cross-sectional area. All right, I think that's enough for the moment. We'll come back and we will do another example with this process in the next video.